All right, howdy, howdy. This is my video showing off the spinning cube animation that I designed. This is based off of Dr. Sanders' spinning donut, but I went ahead and made some changes to it to make it a spinning cube instead. So this is the code below. And we can see that it spins in 3 different dimensions. It spins along the x-axis, the y-axis, and the z-axis. And we can see that it has 6 different faces that are being rendered, depending on which edge is currently closest to the camera, which we'll get into that in a minute on how that works. That is the code. This is the code, sorry. We have our public class spinning donut, because this is Java. We have our main. These are the basic sizes here. So we have our int width of 80 and int height of 40. We have our rotation angles for x, y, and z axes. The A here responds to the x, the y responds to the b, and then the z responds to the c here. This is the cube size, so this is basically like, think about this like the radii of a cube if a cube had a radius. So it goes from the center to the face. We have our projection distance. So think about this just like this is our scale factor essentially. So K1 is our scale factor when we're converting from 3D to 2D. We'll get into a bit later on down there where we actually use our K1. This is our basically our step size. So if we were to make this smaller, we would get even more detail in our cube design, but I mean, you can see we have enough detail. I was kind of messing with this number a little bit, but 0.6 is perfectly fine. This is something that you gave us. It's just the ASCII from lowest brightness to highest brightness. It's in a char array. The period is dim and the at sign is really bright. Medium animation loop, once again, something you gave us. We have a Z buffer and a character buffer. Think about these just like the Z buffer is what is closest to the camera, and we'll be constantly updating this so that it appears to be spinning. And then our character buffer is what we hold to display at each position, basically. So we know actually what to show at each spot on the cube. We are going to set up these buffers basically just by running through the length of them and filling them with zeros and spaces. So pretty standard stuff. These are all just simple grabbing these so we don't have to sit there and recalc. Because if we were to try to recalc multiple different times, it's very, very, very slow. This is the part that gets a bit different than how the spinning donut did it. So spinning donut, we just kind of did everything in this main for loop and it was fine. I did this draw point method because, as we'll see in a minute, I did not want to repeat this logic 6 different times. I rendered each face separately, basically, and then connected them all together into a cube. And then that was kind of the easiest way that I found to do it. Instead of trying to treat the cube as one giant object, treating it as 6 2D faces was a lot easier for me to wrap my brain around. So we'll get into that in a minute. But basically, we have the different faces here. So we have front, back, top, bottom, and then right, left, as felt most natural to me. This little line here, my brother, of all things, actually helped me with. So basically, before it was flickering really badly. It would basically the console would flicker as it would render the new ASCII characters because it would just keep rendering it. This is cool because it would clear the console and then also move the cursor to the top right, and so it kind of locks the cube in space and then also makes it so only like one output at a time is shown, and so you get like this actually very smooth animation of a spinning object instead of like infinitely scrolling and objects overlapping. So I wanted to give a shout out to my brother for that one. So thank you. Anyway, sorry, continuing on. We are going to print out our buffer as ASCII art here. This is also just given by our donut code though. So thank you, Dr. Sanders, for that. We're going to update our rotation angles constantly. So we have our rotate around X and the Y axis at the same speed. We rotate around the Z axis a bit slower though, because it makes the spin look nicer. So it doesn't look like it's in free fall or anything. It looks like it's kind of slowly moving through and rotating for us. And then I kept the delay the same because it didn't really matter too much. This is the new method, though. This is where a lot of my time today went. It was in designing this. So this is draw point. As you can see, draw point takes in a bunch of stuff, including angles, the scaling, the brightness, our cubes x, y, and z, and then the height, the width, the blah 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 blah. We'll get into all this in a minute. But yeah, so essentially, this is doing is we are tracking 3 rotations of our cube. We're tracking the rotation around the x-axis. When we see here that we do so, we don't actually have to worry about the angle of the x-axis because we don't worry about the axis that it's rotating on because that won't change. But for the y, we have the y value times cosine minus the z value times sine. And then for the z, we have y times sine plus z times cosine. And then same thing for the y. When we're rotating the y-axis, we don't worry about the y angle because it's not going to change. So then we have the x1 times cosine plus z times sine. And then same thing for the z-axis. It's negative x times sine plus z1 times cosine. And then finally, same thing for the z. You don't worry about the z-axis since we're on it already. X2 times cosine minus y2 times sine. And then x2 times sine plus y2 times cosine. So this is our translation here. So in order to make it feel like there is like perspective away from the viewer, we set up z post and OOZ to basically give perspective from the viewer. So we do 1 over z position, and then z3 plus 100 to give sort of that distance. And then when we project 3D coordinates to a 2D screen space, we're going to typecast the x position to int, and then take width over 2 plus our scalar times our OOZ that we set up here, and then times our x3. And then same thing for the YP here as well. Another important thing to note is we use negative here because y coordinates are kind of funky, and honestly, in my opinion, coordinates are kind of funky in general. When it comes to rendering, it feels very opposite to me. And so we needed negative for it to actually go the right way. This was kind of throwing me off for a little bit. Anyway, finally, we have a simple check here to make sure that it is within the width of our screen, because if it wasn't, we wouldn't be able to render it properly. And then basically we have a z-buffer test. What a z-buffer test does is we're saying, hey, is this point actually closer than the previous ones? And what that's going to do for us is allow us not to render the incorrect stuff that is there, basically. So essentially what this stops is us from rendering the squares that are in the back, or the faces that are in the back that are hidden, because they can't currently be seen because they're not close to the viewer / perspective. And then we have the luminance stuff that is given to us in the donut code. That's pretty much it. Thank you.